Okay, here's take 3 at trying to explain gravimetric analysis. Next time make sure you press record, and next time you have the headphones plugged in, Dr. Berg. We're looking at the calculations in your booklet. It's page 16, question 4 of your Focus 3 booklet, and this is one of the most challenging questions that I've written for this particular topic because it covers all the sort of tricks you might be thrown with these sort of precipitation sort of questions. This question reads, you've got 50 mils of a liquid fertilizer which has been diluted to 250 mils. Then you take 25 mils of that dilute solution, add it to 200 mils of water, and then you precipitate out the sulfate with excess barium nitrate. Then you filter and dry the precipitate. You repeat the experiment a number of times and record the masses each time. And the question is, as accurately as you can, calculate the percentage of sulfur and sulfate in the original liquid fertilizer. So there's a whole range of steps going on in this paragraph, and I always find it easy to draw a little sketch for myself to understand what's going on in this particular question. And the first thing they've told us that we've got 50 mils of a liquid fertilizer, and they're putting that inside a 250 ml solution. So they're diluting it to 250 mils. I'm going to call that step 1. So we're taking this 50 mils of liquid fertilizer and putting it inside the 250 ml of water inside a volumetric flask, I assume. The next thing is they're taking 25 mils of that dilute solution. So here we go, step 2. They're taking a 25 ml sample of that dilute solution. They're adding 200 mils of water to it and then precipitating out the sulfate. And one of the things to realize is that once you've got this 25 ml solution, that's all the fertilizer we're precipitating out anyway. Adding the 200 mils of water is completely irrelevant to the calculation. Adding the water is not going to change the mass of the precipitate, so it's a bit of a misleading or red herring part of the question. So we're going to ignore that part of the question altogether. So what we're really testing is how many mils or how many grams of sulfate there are in this 25 ml sample. So they add the barium nitrate, which is step 3, and then they filter and dry, which is step 4. Now, once we understand the steps they're doing, we can go through and start making some decisions and ideas about exactly what's going on in this question. Well, the first thing is we've got 50 mils of liquid fertilizer. The first thing is to realize that all that fertilizer has ended up in the 250 ml sample, which means that inside this sample we have got the 50 mils of fertilizer. So if we can calculate the sulfate inside this 250 ml sample, that's the same as the sulfate inside the 50 mils of fertilizer. The next thing to realize is calculating a weight percentage, or percentage of sulfate in the original liquid fertilizer, we've got to divide by the original mass. And we haven't been told the mass of the fertilizer, we've only been told the volume. And when you haven't been told the density of a particular liquid, all you can do is assume that 1 mil is 1 gram, so that 50 mils is equivalent to 50 grams of fertilizer. So we can assume that all 50 grams of fertilizer is inside this 250 mils, and once again, if we can calculate the moles and mass of sulfate in this 250 ml sample, that's the same as the mass and moles of sulfate that were in the original fertilizer. The next big thing to understand is if you take a 25 ml sample out of that 250 mils, they're both going to have the same concentration. Okay, that's a key thing to understand. So when we calculate the mass and moles of sulfate inside this 25 ml sample, we can then quickly and easily calculate the mass and moles of fertilizer in this 250 ml sample because they've got the same concentration. The last thing, by filtering and drying 4 times, that's good. It makes your experiment more reliable, and it means you can pick out errors or pick out outliers. So whenever they give you sets of experimental data, always expect that one of them is going to be an outlier. And as you can see there, the 0.773 grams is the outlier, so we're not going to include it. So just want to recap on the key ideas. First key idea is that these two samples have the same concentration. So if we know the concentration here, we know the concentration in the 250 ml sample. The second idea is that because all the fertilizer was dissolved in the 250 ml sample, that means if we can find the moles and mass of sulfate in the 250 ml sample, that's the same as in the original fertilizer. So let's go ahead and do this calculation now. The first thing we've got to figure out is how many moles, or what's the mass, what's the average mass of our precipitate. And we can do that simply by just adding all those masses together and dividing by 3, and you should get the average mass of precipitate. Next, we want to find how many moles of precipitate we've got, and the reason being is we're trying to find sulfate. If we find the moles of barium sulfate, we also know the moles of sulfate because they react in a 1-to-1 ratio, or the moles of sulfate is 1-to-1 with the moles of barium sulfate, so therefore we can say that the moles of sulfate in that 225 ml sample, that sample we're precipitating, is equal to the moles of precipitate we got out of that 25 ml sample, which is just mass over molar mass, which is that 0.7273 grams divided by the molar mass, and there's our number of moles. Okay, that's the number of moles we got out of the 25 ml sample. But we need to know the number of moles in the 250 ml sample because that's the number of moles in the fertilizer. And this is where that concentration idea comes in. We know the concentration of the 250 ml sample is the same as the concentration of the 25 ml sample, or concentration 1 equals concentration 2. But because concentration is moles over volume, we can substitute now and say that N1 on V1 equals N2 on V2, or N1, the moles in the 250 ml sample, is N2, the moles in the 25 ml sample, which is that number up here, divided by the volume of the 25 ml sample, which is 0.025, times by the volume of the original 250 mils, which is just 0.25. And doing that calculation, we can now say there's 0.031167 moles of sulfate in the 250 ml sample, which also means there's 0.031167 moles of sulfate in the fertilizer. And now it's just a simple case of calculating the weight percent. So we can find the mass of sulfate, which is just number of moles times the molar mass. That tells us that's how many grams of sulfate there were in the fertilizer. And then we can just find the weight percent by dividing by the mass of the fertilizer, times it by 100, and looking at the question, we know it's one significant figure, so that's 6 weight percent sulfate in the fertilizer. The last thing you're trying to find the weight percent sulfur. We know the ratio of sulfur to sulfate is just 1 to 1. Therefore, the moles of sulfur is the same as the moles of sulfate. We can find the mass of the sulfur, similar to how we did it above, and then we can find the weight percent of the sulfur, which is just the mass of the sulfur divided by the mass of the fertilizer, which is 50 grams, times 100, gives us 2 weight percent sulfur in that sample. And that's how you solve that question 4. I'd like you now to try question 5 on page 17. It's a very similar question. It's actually a little bit simpler than that one because there's not so many misleading steps, but it's the same basic idea. And by doing question 5 on page 17, it's pretty much identical to what we did in our experiment 19. And therefore, if you can solve this question, you can solve our experiment question. So pause the video now, have a go at the question, then start it up again because the answer's coming up in just a second. So doing that question 5 on page 17, you've got 1 gram of fertilizer dissolved in 500 ml of water in a volumetric flask. 100 ml of that solution was transferred to a beaker, acidified with HCl and brought to the boil. Don't forget we added the acid to our experiment. We actually added nitric acid to not have any precipitations at all, but adding the acid is so that all carbonates get turned into carbon dioxide and leave the solution, and also so phosphates won't precipitate, so the only precipitate will be barium sulfate. They added barium chloride till the precipitation was complete, i.e. they added excess barium chloride. They filtered it through a pre-weighed filter paper of 0.02 grams, and the precipitate was washed with hot water and ethanol dried in a desiccator, and the final mass of precipitate and filter paper was 0.349 grams. So once again, drawing a little picture, we started off with 1 gram of fertilizer. All that fertilizer went into the 500 ml solution. So if we can find the moles and mass of sulfate inside that 500 ml solution, it's the same as the moles and mass of sulfate inside that 1 gram of fertilizer. They took out a small sample. They took out 100 mils of that sample to do their precipitation experiment, adding the hydrogen ions to remove carbonates and also so phosphates won't precipitate out, and the barium ions to form the barium sulfate precipitate. Don't forget, similar to the previous question, that the concentration of the 500 mils and 100 mils are the same because they're both part of this. They're both samples of the same solution. For the precipitation step, they knew the mass of the filter paper, and we know the mass of the precipitate and filter paper. So the first thing was, what's our mass of precipitate? You should have taken away the mass of the filter paper from the mass of the precipitate plus filter paper. So we've got 0.329 grams of precipitate. We can then say that the moles of sulfate is equal to the moles of barium sulfate in the 100 mils again, and therefore the moles of sulfate in the 100 mils is 1.40 by 10 to the minus 3 moles. Once again, because the two concentrations were equivalent, we can say that concentration 1 equals concentration 2, or N1 on V1 equals N2 on V2. So the moles of sulfate in the fertilizer, which is the same as the moles of sulfate in the 500 mils, remember, because the whole fertilizer went into the 500 mils, we can say the moles of sulfate in the fertilizer was 7.05 by 10 to the minus 3 moles. Now we can convert that to a mass of sulfate, and by doing that, by nanomoles times molar mass, we can find those 0.677 grams of sulfate in the fertilizer. We've got to divide that by the mass of the fertilizer, which was 1 gram. So 0.677 divided by 1 times 100 is 67.7%. But once again, looking at the question, it's one significant figure, so it's 70 weight percent sulfate in that particular fertilizer. So if you got that question right, well done. Let's move on to some other styles of questions. In your Focus 3 booklet, there's a whole lot of converting units questions, and I've had a few students ask me for help with these. So we're going to look at a few of these. And the first one, page 12, question 1a says, convert 15 grams of lead in 200 litres to parts per million. And you've got to realise that parts per million is your mass divided by the total mass times by a million. But the key thing for parts per million is that these two things have to be the same units. It doesn't matter what units you choose as long as they're the same. So we've got to convert 15 grams and 200 litres to the same units. So what we're going to do is say mass of lead over mass of water. We know we've got 15 grams of lead per 200 litres of water, which is 15 grams per 200 kilograms, converting litres to kilograms. That then is 15 grams per 200 times 1,000 grams, because 1 kilogram is 1,000 grams. Now we've got it in grams per grams. We can times by a million and calculate the parts per million.